Good evening. Now you can see a beautiful image of the cycle here which I have downloaded from the internet. This is a cycle which is standing erect at a place, motionless, okay, because no one is of course riding it. It's not automatic as it seems to me, of course, okay. But when it will move, just imagine when it will move along any direction, any path, etc. Will this cycle be as erect as it is right now, or will it undergo a phenomenon called bending? Okay, that's our topic for today, bending of a cyclist. This is an application of Newton's laws of motion chapter, class 11 physics, okay, and it's a continuation of the topic of banking angle and banking of roads, which we had done in the previous video. So let's understand this now in detail. Suppose we have this cycle now which is moving along a path. Maybe it's a straight line path. You can imagine the cycle can move along any path, okay, be it a straight line path like this, okay, be it a curved path, okay, maybe a triangle path, triangular, maybe a rectangular path, etc. In all these cases, these paths are somewhat or the other straight line paths or straight paths, and the cycle will always be erect in these. Erect. It will not go under any bending. But when I talk about a path like this one, which I will just show you now, just concentrate on this path and you will understand what I am talking about. When the cyclist will undergo this path, it will move under this path, the cyclist, which is a curved path, you can see it's a curved ellipse, the cyclist will undergo a phenomenon called bending. Okay, so here the cyclist undergoes the phenomenon of bending. Now why is that so? If you see the circle, it's basically a large curved path like this, and whenever we move along a curved path, this is what you have done before, we require something called the centripetal force. Centripetal force. Okay. Now, generally, if we talk about when a cyclist is moving along this path, say I draw a cyclist here, you can ignore my drawing skills, just concentrate on the content. Suppose this is a cycle here which is moving along this curved path. You would observe that the force of friction is playing a big role here. Between the tires of the cycle and the ground, there is a force of friction. But the centripetal force, which the force of friction provides, is very less, and the cyclist may skid, he may slip. So hence, what is required is some other type of force which will support the cyclist to bend properly, and that force is nothing but your normal reaction. And we already know normal reaction is the force which is perpendicular to the frictional force. So if I illustrate a figure here, and if you just see that this is suppose a path, where I'll draw it even straighter than this because this is a bit curved. So you can just see here. Suppose this is a path a cyclist is taking. It's not a graph, okay? I'm just showing you an axis with respect to a path. So now you can see it. And suppose the cyclist is moving here. This is the tire, okay? And here the cyclist, this is the handle, and here the cyclist is moving. You can just see from this figure that the cyclist has tilted a bit. Suppose let us say that he has tilted a bit with respect to the original path with an angle of theta, and the cyclist has bent along a curved path. So this is a curved path we are talking about. Now here, if I draw the free body diagram, you all should already know that free body diagram is a diagram which shows all the forces on an object. You will see that weight of the cyclist is pulling it downwards, and this is your mg, which is basically your weight of the cyclist. Corresponding to weight, there is another force which is perpendicular to the friction, which we just talked about, the normal reaction. And here I am considering the normal reaction. Normal reaction is denoted by R. We already know that force is a vector, and a vector always is split into its components. So if we split the normal reaction into its components as well, you can see that this normal reaction can be split into a vertical component called r cos theta and a horizontal component called your r sin theta. Okay, so just simple trigonometry. The vertical component is called r cos theta, and the horizontal component of this normal reaction is your r sin theta. Okay, so again, if I draw the free body diagram, the vertical component turns out to be your r cos theta for the normal reaction, and your horizontal component is your r sin theta, and this r sin theta is in the direction of the friction. That's very, very clear. And where theta is the angle of bending. Okay, this theta. Is that okay? So you can take a screenshot of this free body diagram, and then let's understand what is the mathematical part of this. Okay, so I suppose you have taken the screenshot. Now what we can realize here is the cyclist. So I can again write the forces here. The normal reaction, I'll just sum it up, has two components. The vertical one called your r cos theta, and the horizontal one is your r sin theta. Now, as we told you before also, when a cyclist is moving along a curved path, he requires centripetal force, which is provided by the normal reaction. The component of normal reaction, which is the horizontal one, which is your r sin theta, which is the direction of friction. We know the r sin theta is in the direction of friction, and this r sin theta provides your centripetal force. So my first equation which I can get here is the r sin theta, which is the horizontal component, is giving me my centripetal force for bending properly and not falling. What is the formula of centripetal force? You have already done it in this chapter. mv square by r is the formula of centripetal force. If you want me to make a video to derive this formula, please do comment. I would definitely come up with it. This is my first equation. Now if I take a look back to the free body diagram once again, this gives me the whole idea of the scenario. I can see that the weight which is pulling the cyclist down, this weight mg I'm talking about, okay, I'll just point it out with my cursor, that this weight mg, okay, which is pulling the cyclist down, is absolutely equal and opposite to my r cos theta. So I can see that r cos theta and the weight are opposite to each other, and they are balancing each other. That's why the cyclist won't go down under the ground, because the r cos theta is balancing the weight. So that's my second equation. So what is my second equation? The second equation is that r cos theta is balancing the weight. And what is the formula of weight? Mass into gravity, mg. Now what I do is I divide the first equation by second. That means, again look at my cursor, I divide this equation by this equation. Okay, so let's do that. It's an interesting thing. This will become r sin theta. I'll change the color. This will become r sin theta by r cos theta is equal to mv square by r divided by mg. That means we can write it into 1 upon mg. Divided by mg means into 1 upon mg. Alright. Now r and r gets cancelled here. M and m gets cancelled here. What I can get? Sin theta by cos theta is tan theta. So here what I get is tan theta is equal to v square by rg. Isn't it? So what I conclude from here is, what is theta? Whenever a trigonometric ratio is equal to some value of the theta is the inverse of the value. So theta is tan inverse v square by rg, and that theta is my angle of bending. Okay, that theta is my angle of bending, this angle which I was talking about. So the value of this angle comes out to be tan inverse v square by rg is the value of this theta, which is the angle of bending. That means the cyclist bends by this angle in order to avoid slipping, so that he gets the centripetal force. Okay, now if I just go through this formula once again, I can derive two results from this formula. Just looking at this formula, that theta is tan inverse v square by rg. We know that theta, if it is equal to tan inverse v square by rg, this formula, that means the theta is directly proportional, you can see from this formula, to v square, that is the velocity of the cyclist. Okay, theta is inversely proportional to the radius. of the tire. Okay, this is the radius of the tire. That means what I can conclude is, if I want theta to be a large value, radius must be very small. Okay, because theta is inversely proportional. So if the angle of bending has to be less, that means the radius has to be very small, or the turn has to be very sharp. Okay, and in the same way, if theta has to be large, that means the bending has to be large, the velocity, because theta is directly proportional to velocity square, the velocity also must be large. Okay, so as your formula says, theta is equal to tan inverse v square by rg. This shows that theta is directly proportional to v and theta is inversely proportional to r. That means if a large velocity is there, I would get a large bending. Okay, a cyclist who is going faster would bend more, and on the other hand, if the velocity is small, sorry, the radius is small, that means the cyclist who has a sharper turn of the path will bend more. So you can be given this analytical question, which cyclist will bend more? Okay, and this is the simplest way of solving it. Okay, so that's what we have done for bending of a cyclist. With this we close off the class. I hope you enjoyed the video. I will soon be coming up with more parts to this chapter and other chapters of all other subjects. You can read the description if you want information of my channel. I have detailed it a bit. Okay, so please go through it and please subscribe the channel. Do not forget to like the videos and share it, and press the bell icon for the upcoming notifications as well. So stay safe, take care, thank you, and good luck. Bye bye.